Welcome to Module 1 of this course on highway engineering. In this session, we will explore the fundamental principles that guide the planning, design, and evaluation of highways. Highways are more than just roads, they are the backbone of transportation systems, connecting cities, rural areas, industries, and people. Without an efficient highway network, economic growth, trade, social interactions, and even safety can be severely compromised. Our discussion in Module 1 will center around the engineering aspects of highways, beginning with route location and surveys, moving on to geometric design and pavement design, then addressing interchange design and spacing, highway information systems, freeway networks, and finally, safety considerations. We will also touch on the importance of road cross-sections as they influence usability and long-term performance. Let's begin with the starting point of every highway project: choosing the right route. 1. Engineering aspects of highways. The engineering aspects of highways cover the scientific, technical, and design-related processes that ensure a road is functional, durable, safe, and cost-effective. A highway engineer must balance several considerations, including topography, how the landform affects alignment, grading, and earthwork. Traffic demand, how many vehicles will use the road and what kinds: cars, buses, trucks. Economy, how much the road will cost to build and maintain, relative to its benefits. Environment, minimizing adverse effects on ecosystems, water bodies, noise levels, and nearby communities. Safety and comfort, ensuring users can travel with minimal risk and in acceptable conditions. Engineering decisions on highways must integrate these diverse aspects. If any one is neglected, the result may be poor performance or even failure of the road system. 2. Route location and survey. The first practical step in highway engineering is determining where the road should be built. This involves route location and survey. 2.1 Reconnaissance survey. The reconnaissance survey is the initial exploration of possible routes. Engineers collect general information on landforms, mountains, valleys, rivers, existing roads and settlements, soil types and drainage, environmental constraints such as forest or wetlands. The purpose is to identify feasible corridors for further detailed study. 2.2 Preliminary survey. Once possible corridors are identified, preliminary surveys narrow the options. Tools such as aerial photographs, GIS mapping, and drone surveys may be used. Data is collected on slopes and gradients, length of route, estimated cost, accessibility to key towns or facilities. The result is usually 2 or 3 possible alignments for comparison. 2.3 Final location survey. The final survey provides precise details of the chosen alignment. This includes centerline alignment marked on the ground, detailed topographic mapping, geotechnical investigation of soil and rock conditions, hydrological studies for drainage and water crossings. Modern technologies such as GPS, total stations, and geographic information systems greatly enhance the accuracy and efficiency of these surveys. 3. Geometric design of highways. Geometric design refers to the physical shape and layout of the highway. It ensures that the road accommodates vehicles safely and efficiently under expected traffic and environmental conditions. The major elements of geometric design include 3.1 Cross-sectional elements. A standard cross-section includes carriageway width, the actual width for vehicle movement, varying from 2-lane rural roads to multi-lane expressways. Shoulders, spaces beside the carriageway for emergencies, breakdowns, or non-motorized traffic. Medians, separating traffic flows on divided highways. Side slopes and embankments, ensuring stability of the roadbed. 3.2 Horizontal alignment. This deals with the curves and straight stretches of the road. Important considerations are radius of curvature, larger radii are safer at high speeds. Transition curves, easing drivers into and out of curves. Superelevation, banking of curves to counteract centrifugal force. 3.3 Vertical alignment. This refers to gradients, slopes, and vertical curves. Key design aspects include maximum gradient, limited to ensure heavy vehicles can climb without excessive difficulty. Crest curves and sag curves, designed to provide adequate side distance for safety. 3.4 Side distance. Side distance is critical for safety and includes stopping side distance, minimum distance required for a driver to stop safely. Overtaking side distance, distance needed to pass another vehicle safely. By balancing these elements, engineers ensure comfort, safety, and efficiency for drivers. 4. Pavement design. The pavement is the structural layer of the highway that directly supports traffic loads. A poorly designed pavement leads to early deterioration, potholes, and high maintenance costs. Types of pavement. There are two major types. Flexible pavements, made of bituminous or asphalt layers. They distribute loads gradually through successive layers of subbase, base, and surface course. Rigid pavements, made of concrete slabs. They distribute loads over a larger area due to slab action. 4.2 Pavement design factors. Design depends on traffic loads, both the number and weight of vehicles. Subgrade soil strength, poor soils require thicker or improved pavement layers. Climate, temperature variations, rainfall, and freeze-thaw cycles affect performance. Durability and cost, balancing initial construction cost with long-term maintenance. 4.3 Structural design. Pavement thickness design uses methods such as empirical methods based on road test data. Mechanistic empirical methods considering stresses, strains, and material behavior. Ultimately, the goal is to provide a pavement that lasts its design life, usually 15 to 30 years, with minimal maintenance. 5. Interchange design and spacing. In urban and freeway context, interchanges replace intersections to maintain uninterrupted traffic flow. 5.1 Types of interchanges. Diamond interchange, simple, commonly used for low to moderate traffic. Cloverleaf interchange, handles high volumes without signal control but requires more land. Trumpet interchange, suitable where a highway terminates at another. Directional interchange, complex, used for major highways with heavy turning movements. 5.2 Spacing of interchanges. Spacing must be carefully planned. Too close, and drivers have insufficient distance to weave, merge, or exit. Too far apart, and accessibility is compromised. Standards vary, but typical minimum spacing in urban areas is about 1 to 2 kilometers, while rural freeways may have 3 to 5 kilometers between interchanges. 6. Highway information systems. Highway information systems are computer-based tools that assist in planning, design, maintenance, and management of highways. They are often part of a broader Geographic Information System (GIS). 6.1 Applications. Storing and managing data on road networks. Traffic analysis and forecasting. Pavement condition monitoring. Environmental impact assessment. Optimizing maintenance schedules. By integrating spatial and statistical data, it helps decision-makers allocate resources more efficiently. 7. Freeway networks and safety. 7.1 Freeway networks. Freeways are high-capacity, access-controlled highways designed for uninterrupted flow. Their networks must be carefully planned to connect major cities and economic centers. Provide redundancy so that traffic can be redistributed in case of blockages. Balance national, regional, and local needs. 7.2 Safety considerations. Highway safety is a crucial aspect. Common measures include adequate lane widths and shoulders. Median barriers to prevent head-on collisions. Guardrails at dangerous sections. Road markings, signage, and lighting. Intelligent transport systems, ITS, such as speed cameras and traffic sensors. Road safety audits are often conducted during design and after construction to ensure hazards are minimized. 8. Different cross-sections of roads. The cross-section of a road determines how space is allocated for vehicles, pedestrians, and drainage. 8.1 Rural roads. Typically simple, with 2 lanes, shoulders, and side drains. 8.2 Urban roads. Often include sidewalks, cycle tracks, parking lanes, and wider medians. 8.3 Expressways. Feature multiple lanes, wide medians, service roads, and controlled access. Cross-sectional design must balance cost, land availability, and expected use while ensuring safety and durability. Conclusion to Module 1. We have covered the essential engineering and design aspects of highways. We started with route location and surveys, which determine the best possible alignment for new roads. We then explored geometric design, which shapes the physical form of highways, and pavement design, which ensures structural durability. We discussed interchange design and spacing to manage traffic flows, followed by highway information systems and freeway networks. Safety and different road cross-sections were highlighted as critical to functionality and user comfort. In Module 2, we will shift focus to the construction and maintenance aspects of highway engineering, covering drainage design, culverts, construction equipment, and the integration of field and studio practice.